Okay, so you should be seeing my title slide. Over the past couple of years as a student, I have been contributing to the commissioning of the Fizeau Interferometric mode at the Large Binocular Telescope. The LBT has come up a few times in this conference, but again, if you're not familiar with the LBT, or to refresh your memory, the LBT is a telescope on a mountaintop in southern Arizona. This is a picture of the interior of the chamber from a few years ago before it became cluttered with instruments. And what's particularly important and unique about the LBT is that it consists of two 8.4 meter primary mirrors on a common mount. So this is an image looking down now on the primaries from a few years later. The LBTI instrument is, if you can see my cursor, this instrument in the middle between the two mirrors. And as of now, today, is the only instrument at the LBT that can combine light beams from both primary mirrors onto the same detector. That may change some years into the future, but as of now, the LBTI is the only instrument at the LBT that can do that. To get an understanding of why the Fizeau mode is important for us, imagine that we have a target on the night sky, and we have an entrance pupil defined by the primaries of the LBT. We have a bunch of optics, and then there's an exit pupil upstream of the detector. If we maintain strict proportionality between the entrance and the exit pupils, we fulfill the sign condition so as to put the center of the coherence envelope throughout the detector so that we can actually perform interferometry on a wide field of view or relatively wide field of view on the detector and always maintain a strict, a simple convolution relationship between the perfect object and the telescope PSF. This is in contrast to, say, the alternative Michelson mode or the nulling mode. And this really is what allows us to turn the LBT from an 8-meter telescope into a 22.7 meter telescope with a strange mask over the big primary. The LBT PSF in Fourier space has this characteristic 3-lobed structure. The original proportions of the LBT were designed in the 1980s so as to maintain a continual sampling in Fourier space across these 3 nodes. Just by way of terminology, I'm just going to call the amplitude of the Fourier transform the MTF, or the modulation transfer function, and then the phase is the PTF, or the phase transfer function. This is a cross-section through the LBT MTF. Black is just a model here at a wavelength of 4.05 microns, and then blue and red are empirical MTFs from an on-sky observation of the bright star Altair. Blue is when the phase was actually controlled, so in this context, that means where the vertical striping through the Airy PSF to create an LBT Fizeau PSF, that vertical striping is kept frozen, whereas if there is no phase control, then those jail bar or vertical stripes move back and forth according to differential piston between the two telescopes, which the AO systems are not sensitive to. This MTF is particularly interesting for us who are interested in studying planet formation because, among other things, in those high frequency lobes, it samples detail equivalent to distances of a few AU for distances out to Taurus, the nearest large star forming region. This is a schematic of the instrument where if you imagine that the beam from the left-hand telescope is in red and the right-hand telescope is in blue, the beams are combined. They go into a cryostat containing 2 science detectors. Elmer-Cam is at 1.5 to 5 microns, and then Nomic is 8 to 12 microns. And then there's a phase detector that does fast readouts, which are fast Fourier transformed, so as to calculate the tip, tilt, and piston corrections to send to the mirror with a star there at a rate of around 1 kilohertz. Now the LBT it was designed back in the 80s, and it's been a long time in coming, but the Fizeau mode has only in the past 10 years seen the first on-sky milestones of the commissioning phase. It was a decade ago that the first seeing limited Fizeau fringes were seen using an older cryostat up at the LBT. After both telescopes of the LBT were outfitted with deformable secondary mirrors, it was actually possible to AO correct the PSF, but this was before any phase control, so this image here has been plucked for symmetry in the fringes. And then phase tracking was first implemented the next year. Phase tracking was equally significant for the nulling and Fizeau modes of LBTI because the whole phase tracking system as of now is blind to whatever interferometric mode you're in. Now for a time, Fizeau kind of took on, it was not of primary scientific importance for some years because the core scientific purpose of the LBTI was to take a survey of exozodiacal disks so as to characterize the exozodiacal luminosity function down to a sensitivity of a few solar system zodies. And that was the host survey. So if you're interested in that, see recent papers by Steve Ertel, E-R-T-E-L, who's at this conference. But the next year, the first peer-reviewed papers, both in nulling and Fizeau mode, came out. The Fizeau mode observations were done without any phase control. This was of the Jovian moon Io. And then host observations came to an end in the spring of 2018. It was very shortly after that when we took the first phase-controlled filled-aperture Fizeau observations of the star Altair. In the couple of years since then, I've spent a fair amount of time writing code not only to reduce that unique data set, but also to remove non-common path aberrations in the Fizeau mode, which are particularly pernicious because if you imagine these are all the elements in the cryostat, so this is downstream of the telescopes. In order to carry out Fizeau with LBTI, for the science channels, you have to combine both pairs of telescope beams on science detectors at the end of those blue paths. And then if you want phase control, you also have to co-align the beams along that orange channel. And these paths are much more non-common than they would be in nulling mode. So doing the Fizeau mode in aberration-free form takes a little bit, it takes a little bit extra work. If you don't control for those aberrations, you get these differential tilt, and phase errors manifest on the science detector, which the phase detector is blind to. And of course, the AO systems are blind to them as well. So if there's just one message that I want to leave you with, it is that the LBT Fizeau mode at long last is maturing. It represents really the first ELT capable platform along what is today the longest Fizeau baseline in the world in the thermal infrared at 22.7 meters. Just as a footnote at the end, I would say that the nearest term technical improvements that are on the horizon are, first of all, a phase detector upgrade, which could bring a lot more targets into the possibility of taking observations with phase-controlled Fizeau, possibly down to a K-band magnitude of 9. There is an issue involving phase centering that is necessary to overcome for the completion of a non-common path aberration removal loop. So if you have experience with fine phase centering, I'd be happy to talk with you, or you could speak with Narsi Reddy Anugu. He's also at this conference and is the new postdoc in LBTI. And then finally, we also have some ways to go in reducing the amount of overhead that is lost due to phase loop openings. And there are different strategies for doing that. But phase loop openings still represent a fair amount of lost time in Fizeau observations. And so with that, I will stop and take any questions.
Valentin, you're muted.
I see somebody is typing, but I encourage, the question is still not up, so please type faster. In the meantime, I'll take advantage to ask two questions. First, what about the access to this facility, to the VLDI? And second, you had a plot where you had the angular resolution in physical units. But I see that you can do Fizeau only with fairly bright targets. So how many actually stars are bright enough in Taurus to do that?
So so for accessing, so the LBT is run by a private consortium involving, so there's Germany, the LBTB, Italy, ENAF, the University of Arizona, and then a collection of other US-based institutions. So it is a private facility, but if one can strike up a collaboration with people within LBTI, that could potentially be possible. I would point you probably to Steve Ertel for those kinds of discussions. Yes, you point out that it is true that only very bright targets are currently accessible to phase-controlled Fizeau. So by bright, I mean K-band magnitudes of 4.5 or better. That does not mean, though, that you cannot do any Fizeau on other targets. There are targets that are dimmer or are resolved, so we cannot track the fringes on them because they're not point-like enough. And depending on the science that you're doing or the sensitivities that you're interested in, you could do Fizeau with AO correction, but with no phase control.
Okay, fine. Let's bring that to the Slack channel. Denise is asking if you have estimated the gain in contrast of the Fizeau mode compared to the non-interferometric imaging with the LBTI.
So I do have a paper that's going to be submitted soon where I try to carry out a pioneering reduction of high contrast imaging using the Fizeau PSF. This is based on some ideas that were proposed by a gentleman named Patru over the past couple of years, where he said that there could potentially be a gain in sensitivity if you use the LBT Fizeau mode as opposed to direct imaging. Right now, we still are limited by the proportion of frames that are usable because for those particular observations of Altair, the phase loop kept opening. And if with some scaling relations, I do see a comparable gain between the Fizeau mode and the filled aperture direct imaging mode. But with more complete data sets and with more computational ability to really inject the full Fizeau PSF with fake planets, we'd be able to put better constraints on that. So that's still kind of a work in progress.
Thank you.